In this video, we will go over the second part of section 4.2, antiderivatives as area, and we're going to look at something called Riemann sum, okay? Remember the ones that we went over in part 1. Let me go back to that one real quick. When we graph the functions, we had either a straight line constant function, a linear function that was another straight line, but the areas that we got using these functions were giving us just like area of a triangle or area of like a rectangle, or worst case scenario, we saw an area of a trapezoid, right? But we still knew the formulas, the geometry formulas to find those areas. But in this video, we're going to look at a curve, things like maybe number 7, I graphed it and screenshotted the graph for you on this note over here. Notice how what they're going to ask you to do is find the area in between 1 and, where's 1? This is 1. And 16. 16 is right up here, right? So if I shade the area that we want to find, this isn't a triangle or this isn't a rectangle. This isn't a trapezoid. This is a shape with this curve as a side, right? So there is no area formula that will let us find the area of this shape, okay? So in that case, what do we do? What we're gonna do is we're gonna cut that area in rectangles. I'm gonna just cut it in enough rectangles and find the area of the rectangles and just add them together. So here, we're not getting the exact area. We're actually getting the approximate area. As you know, the rectangles, let me show you what I mean by that. So we're going to go from 1, from this point, all the way to 16 in that last example that we're going to go over together, right? So what we're going to do is, say I said I'm going to do a 5 subinterval. So 1, 2, 3. So after 3, I'm going to go ahead and, until 3, I'm just going to go ahead and draw a straight rectangle right here. And then from here to 4, 5. This is 5, 3, 4. What am I doing? Hold on. 1, 2, 3. Oh, I need it a little bit bigger. Sorry about that. I need this rectangle. And we'll talk about the width of this rectangle together too. But this one will go all the way up to this point. And then from 4, I'll go up to here. And then go over 3. 1, 2, 3. So up to 7. And from this point, I'll go 1, 2, 3 to 10, but I'm going to go ahead and use that point. And almost done. They're going to ask you to do 5 subintervals. So far, I got 1, 2, 3 subintervals graphed. 1, 2, 3. This one's going to go over here. And then the last one will go from this, not that point. That's not on the curve. As you notice that I'm using the points on this curve to draw these rectangles. So what we're going to do in this lesson is find the area of these blue shaded rectangles. How many rectangles do I have? I have 1, 2, 3, 4, 5. That's what they mean by 5 subintervals. They're going to ask you to draw 5 rectangles and find the area of them and add them together. And that's how we're going to estimate the approximate area under the curve. And you know it's not the exact area under the curve, because notice this piece is not included. I mean, that's still area under the curve. That's not included. And this is not included, right? Those green pieces are not counted. And also, notice that this part, the purple, that wasn't under the curve, but we're still using it to estimate the area. That purple side or that purple side. So you know it's not exact. This isn't exact, but this is going to give us a good approximation of the area under this curve. And as you can tell, the smaller these rectangles are, and these rectangles are all going to have the same width. But as we make these width infinitely small, we will be able to find the exact area under the curve, and we'll talk about that in next section. But right now, what we're going to do is, the idea of this lesson is we're going to cut this area under the curve into not too many, but like reasonably small number of pieces so that we can find the area of these rectangles and add them together. Good news is that area of a rectangle is super easy to find, right? You just do length times width, and you add those length times with those areas together, and that's how we're going to find it. I think for me, the harder part is really drawing this picture and figuring out what's the length and what's the width of these rectangles. Once you can tell what the width and what the length of these individual rectangles are, finding the areas of them and adding them is not going to be difficult at all, okay? So for daily problem for 4.2, section 4.2, what I did was, I'm giving you this one. Find the left Riemann sum of the function f of x equals 25 minus x squared on the interval 0 to 5, divided into 5 subintervals. Now, this will be kind of challenging if you don't have a picture, but this is the first time I was trying this. So I'm going to give you what we are really doing. We're approximating the integral from 0 to 5 of 25 minus x squared dx by computing the area of each rectangle. Guess how many rectangles I have here for you? 5 subintervals, so you have 1, 2, 3, 4, 5. And what I mean by left Riemann sum, these rectangles are created by the left endpoints all on this curve, okay? So in our class, we're just going to do the left Riemann sum. We're not going to look at right Riemann sum or the midpoints, but those are also fine too. But we're just going to look at the left Riemann sum in this very short lesson. So what I want you to do on your 4.2 daily problem is find the area of these 5 rectangles, and add them together. As you know, are we going to be overestimating the area or underestimating the area? Or is it going to be exactly the same as the area? Notice how the orange pieces are sticking out of this curve. The orange pieces are sticking out of the curve. So if you try to type that into your calculator, you're going to get an exact answer, right? You're going to get the exact area under the curve. Like if you're typing this into like your TI-84 calculator, that's not what I want in this assignment. I want you to find the rectangle's area and add them together. The answer that you will get will be bigger than the actual exact area. So that's the idea. So I guess I'm going to have to talk to you about how to draw this picture and how to find the length and width. Because I feel like if you get the length and width, you can find the area of a rectangle easily and just add them together, right? So let's talk about that. Let me go to the notes. I posted the blank one here for you. This is what we're going to go over. Just 3 pages, just 3 examples. But you know, they may take a little bit longer time because we have to draw and everything, okay? Alrighty, let me go back. Oh, whoopsie. Let me go back all the way up to the top page. The Riemann summation. In Riemann summation, rectangles can be used to approximate the area under the graph of a continuous function. And we say approximate because take a look. If you're interested in finding the area from A to B, like say this is A, which is x1 they said, and this is B. If you want to find the area under this curve from this point to that point, what I really want is everything that I'm shading in purple right there, right? Now, the rectangle method will work, but notice how some rectangles are actually bigger. They're above this curve. And areas like these, this much and that much, is not really getting added, right? So it's not going to be the exact area, but it's going to give us a good approximation, okay? So in the following figure, a closed interval, A to B, is divided into how many subintervals? How many rectangles do you see? 1, 2, 3, 4. So we have 4 subintervals, right? 4 subintervals. And each of them are having the same exact width. You notice from x1 to x2, and from x2 to x3, and x3 to x4, these widths are all the same. And we use the notation delta x, change in x, to describe the width. And how do we find the width? Using the endpoints of interval. Notice we're going to find the length of A to B. How long is from A to B? You're going to first subtract B minus A. And how many subintervals do we have? We have 4 equal subintervals, right? So you're going to divide by 4. So this is how you're going to tell the width of a rectangle, okay? So if you wonder, what's the formula for width of a rectangle? That's what it is. So suppose that I'm going to ask you to find the width of a rectangle, a rectangle. each of these rectangles from, just going to make up a number, 4 to 32, okay? Say that you're looking at an interval from 4 to 32, and then I tell you, I'm just going to make up a number, okay? I want 6 sub-intervals, okay? Then what's going to be the delta x? Well, in other words, what's going to be the width of each of these rectangles? That's going to be, you first subtract the endpoints, 32 minus 4, and what do? You divide by the number of sub-intervals that you have. So that's going to be what? 32 minus, I hope these are nice numbers, 32 minus 4, 28 if I divide that by 6. Hey, it's not really so nice. It's okay, but that's approximately 4.6 repeating, right? But I'm not going to do that. I'm probably going to give you like numbers that work out nice. All right, how about I change it to like what, 4 or like 7. All right, I'm going to change it right now. Sorry. What if I ask you to do like 7 sub-intervals? Then you're going to do 32 minus 4, and which is 28, and divide that by 7. You will get 4 as the width of a rectangle, okay? So that's how you find out the width of a rectangle using the endpoints of your interval, of your closed interval. You subtract these endpoints and divide by the desired number of sub-intervals, okay? Now, height of the rectangle. Now, let's take a look, though. You have 4 rectangles. Rectangle number 1, rectangle number 2, rectangle number 3, and rectangle number 4. Notice they all have the same width. It's the same. That's how we're going to make these rectangles. We're going to make them so that they have the same width. But what about the height? You see, who's the tallest? Rectangle number 2 is the tallest, right? And who is the shortest? Rectangle number 4 is the shortest. You notice they're all different. Rectangles have different height. So how would you write their height? I mean, height is from 0, this point, all the way up there. And this point right there, the y, that's simply the y value of this function. So the height of the rectangle for rectangle number 1 is f of x of 1. The first y value of this x value, and then the height of the second rectangle is going to be f of x of 2, and so on, right? But notice, are they all the same? No. As we can see, the height of rectangle number 2 is taller than the height of rectangle number 4. So these are all different. So notice that to find the height of rectangle, you're going to actually have to evaluate the function value. You plug in the x value, you plug in your left point, the point on the left of your rectangle into the function, and then that's how you can find the height of the rectangle. So in this case, how many different heights are you going to have? You're going to have 4 different heights. Now we're done talking about width and height. Now let's talk about the area, okay? Now, if you're finding the area of each individual rectangles, let me do the area of the first rectangle, okay? Area of the first rectangle will be length times width, or I'm going to do height times f of x1 times the width. What's the width? Delta x, right? So that's the area of the first rectangle. I may probably need more room over here. Let me move this guy over here a little bit. Now let me do the area of the second rectangle. F of what? X of 2 this time. But you still multiply that by delta x, which is the width, right? So that's the second rectangle. And let's do the third rectangle. The third rectangle's area is f of x of 3 times what? Same width of delta x. Now I got 4 areas added up so far, right? Now I just need my fourth one. Fourth area is f of x of 4 times what? Delta x. Now, this is just a notation for sum of 4 rectangles, right? Sum of areas of 4 different rectangles. Suppose you divide this into more pieces, like 16 rectangles. Then you have to find the area of 16 rectangles and just add them all together. What we just did is called a Riemann sum. Okay, it's sum because we're adding them, right? Now, it's a long, if you write it out as like a sum of like 4 different things, it's long. But what you can do is you can use this summation notation. I know you saw this summation notation before. You used it before. It's the sigma notation, and where we use that Greek capital letter sigma. So let me go ahead and rewrite this using that sigma notation, right? All right, hold on. So write down this sigma notation, and then write the index. I goes from 1 to 4, and I represents the number of the rectangles here. So you see x goes from x sub 1 goes from, the subscripts goes from x1 to x4. You notice that? So I is called the index. It's going from 1 to 4. If I had 10 rectangles, I will go from 1 to 10, but it's going up from 1 to 4. So the index of this sigma notation is from I equal 1 up to 4. Now, everything else, you see how they had a pattern? We were multiplying f of x sub I, and that I was what was changing. I went from 1, 2, 3, and 4. So you can just write I in general, but we were always multiplying them by what? Delta x, because they all had the same width. So how do we read this notation? We read it as the sum of the product, right? Because we multiply length times width to find these areas. Sum of the product, x of f of x of I, from what number to what number? From I equals 1 to I equals 4, because I represented the number of rectangles. We had 1, 2, 3, 4 rectangles. And that's how you read it. This is how you read the summation notation. So let's actually work with a summation notation, write something backward, okay? So if you were given a summation notation like this, what does this mean? What does this mean? What we have is, let me go ahead and just write over here. We have a sum of I goes from 1 to 5. Now, tell me, how many rectangles do we have? We have 1, 2, 3, 4, 5 rectangles. So we're going to have 5 terms getting added together. And h of x of I times x delta x. This is the area. This is the height times the width. So let's write the first term. Replace the I with 1. That's going to be the first term. So the first term is going to be h of x of 1 times delta x. All right, that's it. That's the first term. Let's see if I have 5 colors. Next one, h of x of what? 2 times delta x. And notice they all have delta x. So I don't need to change anything about delta x. Next one, h of x of 3 times delta x. Now we need to do how many more times? 2 more times. Next one, plus h of x of 4 times delta x. And what number tells us when to stop? Because, I mean, we can go on forever, right? Which number is telling you to stop? They want you to stop at 5. Stop at 5. And this number down here is telling you to start at 1. Okay? So the very last term is going to be h of x5 times delta x. So that's how you can rewrite it without summation notation. So if you imagine this, what they are doing right here is they are adding 5 rectangles, areas of 5 rectangles to estimate the area under the curve of this h of x. Okay? Alrighty. So let's actually graph some curvy functions and then do this Riemann sum. Okay, let's number 6 and number 7. I just have 2 examples, but number 6, we're gonna actually do like 3 different parts here. So let's take a look. Number 6, consider the graph of f of x equals square root of 4 minus x squared over the interval 0 to 2. This is a quarter circle of radius 2. I want you to use Riemann sum to approximate the area under the graph using 4 equal sized sub-intervals. All right, that's what we're going to do first. We're going to do part 8. 4 equal sized sub-intervals. Hey, I don't like my handwriting. subintervals. We'll do A, 4 equal size, and then what do they want? Then 8 equal size subintervals. Oh my goodness. So for that part, we're going to have to draw how many rectangles? We're going to have to draw 8 different rectangles. 8. I don't think I need to write down, because we can assume these rectangles are going to have equal width, equal size subintervals, equal 8 subintervals. I don't like how they say equal size. I mean, that's okay. We're not going to get equal size rectangles, but these intervals are going to be the same size. The intervals are the width of these rectangles. Then we're going to use part C, use the geometry to find the area under F over 0 to 2. Now, here's the thing, though. They said use geometry. Geometry means what's the area of a triangle, area of a rectangle, area of a trapezoid. But what shape is this? They're saying this is a quarter circle. You know the area formula for quarter circle, or for a circle. That's going to be pi r squared, right? But if you want a quarter circle, that's simply going to be pi r squared quarter, like 1/4 of that. And we already know that the radius is what? 2. They gave that to us, but we can also graph this ourselves and figure that out. But this is very nice. They gave this to us. So you know what? Let me go ahead and just figure that out in this tiny little margin first. 1/4 times pi times what number squared? 2 squared. That's going to be what? That's 1/4. This is going to be 4 pi. So it's going to be approximately what? 3.14 units squared. That's going to be the exact area. So using geometry, just because this graph happened to be a quarter circle of radius 2, we know the exact area has to come out to be 3.14. Now, which one, A or B, 4 equal size subintervals or 8 subintervals, which one do you think will give us a closer approximation? And we'll see that. We're going to find the answer for A and B, and then compare this value to our approximations, okay? All right, first, let us draw this f of x. F of x equals square root of 4 minus x squared. And thank goodness they gave us an interval from 0 to 2. Okay, so I'm going to go ahead and just graph something like this. When f is 0, I'm just going to do it old-fashioned way. F is 0. I'm going to have 4 minus 0 squared, and that's going to be square root of 4, which is 2. So at 2, I'm going to have a point at 0, I'm going to have a point at 2. So 0, 2 is a point. Now, what about another one? F of... I guess I can do infinitely many points, but who has time for that? So let me do the next point, 1. So I'll do 4 minus 1 squared. Ew! Square root of 3. So suppose we plot a point at 1 square root of 3. What's that approximately? Also that I can just kind of have a point there. Square root of 3 is approximately... No, when I type in square root of 3 on my calculator, guys, you know what it's doing? It's giving me square root of 3 back. Hello? Square root of 3, can you please give me square root of 3? What's that approximately? Like 1.732, okay, 1.732. I memorized it. It's like 1.732 ... Okay. So somewhere like over here, okay, at 1. Like something like that. Okay, now what about f of 2? What's that going to be? 4 minus 2 squared. That's going to be square root of 0, so that's 0. So I'll have a point at 0, 2. And, you know, I got a graphing calculator. We can try to graph it, and in our class, we can use graphing calculator any day. Square root of 4 minus x squared, wasn't it? X squared. And I'm just going to look at the graph in the first quadrant. Where are you, graph? Here we go. So you're looking at me zooming in like crazy. So, if I'm trying to make equal scale, trying to make my equal scale. You see what they mean by, hey, this is a quarter circle. It is a quarter circle. So what I want to do is I want to draw a perfect quarter circle. But you can use your graphing calculator just to kind of get the picture first. So here's a graph. Let me try to graph this. That's where we kind of touch that. Oh, that looks bad. That's kind of where we touch that 1.77732. So this is a picture. Now, what do they want you to do? They want you to cut this quarter circle into 4 equal size subintervals, right? So the subintervals, we know we want 4. So let's actually find the width of these rectangles. Remember, delta x is the width of a rectangle, and that formula is b minus a divided by the number of subintervals, right? Let's actually just plug in the numbers. So let's subtract the endpoints. I'm doing 2 minus 0 divided by how many subintervals do we want? 4. So that's going to be 2 over 4. So width of a rectangle is going to be half. So this is 1. So every half point, I'm going to draw a rectangle. So take a look. From this point to that red point, I'm going to draw a rectangle. Here is a beautiful rectangle. From this point on the curve to 1, I'm going to draw another rectangle. On the curve again, and you see how I have to stick out of this curve because I need to draw a rectangle. That's my third rectangle. And from this point on the curve, straight out and straight down, I drew the fourth rectangle. You notice that I have 1, 2, 3, 4 rectangles over here, and each delta x is equal to half. So the width of these rectangles are all half. All right, now the harder part, guys. I know because we have a formula for width of a rectangle, that's not that hard. But the thing is, the height of the rectangles are all different, right? So let me go ahead and I did say delta x is 1/2 there, but I think I can just get rid of that because I'd rather write the x values here. X value here is 0, x value here is half, x value here is 1, and x value here is 2 3/2, and then the x value over here is 2. Now we're going to evaluate the function values so that we can find the height. So first find f of 0. Then you're going to also find f of 1/2. And then you're going to find f of 3/2. And then the last endpoint that we're stopping at is f of, I missed the 1. Sorry about that. This one should be f of 1. And then the last one will be f of 3/2. So where did I get these numbers from? These are the left endpoints of my rectangle. Okay, notice I'm not doing f of 2. Why not? Because do I have a rectangle to the right of it? No, I don't. So I don't need that rectangle. I just need to evaluate these values because these are going to give me the heights of each of these rectangles, okay? So let's plug in f of 0. We got that to be 2, right? Didn't we plug that in and got 2? So the height, this is the height number 1. This is the I won't write it. This is the first height. Now, let me plug in half into the function and see what the y value is. 4 minus half squared. Oh, please be a nice number. Please be a nice number. I'm grabbing a calculator and typing that in. Square root of 4 minus 1/4, right? 1/4. You know, it's giving me decimal. I don't want that. So I'm going to do this by hand. So it's going to be 4 square root of 4 minus what? 3, not 3. Don't go too fast. 1/4, right? So that's going to be square root of 16 over 4 minus 1/4. I'm going to have to move these guys down a little bit. That will give me square root of 15/4. And if I try to simplify this, I will have square root of 15 on the numerator, and the denominator can come out as 2. Okay, yay! So I got that. So that is what we just found is the second height, right? The second height of the second rectangle. the height of the second rectangle. Now, if I plug in f of 1, I did that earlier, and that came out to be square root of 3. Now, let's do the last one. If I plug in 3/2 into that function, that's going to be 4 minus 3/2 squared. Nothing we cannot do without a calculator. That's going to be what? 16 over 4 minus 9 over 4, which is, 7 over 4. Therefore, square root of 7 over, not 4 in the denominator, square root of 4 comes out as 2. Yay! So, I had to do 4 substitutions. Why? Because I needed 4 different heights for 4 equal size, equal width rectangles. So I'm going to go ahead and now find the Riemann sum. I'm going to find the area now. So why don't we bring in our fancy sigma notation. So sum is I goes from 1 to 4, okay, of f of x sub I times delta x, that Riemann sum is equal to, first one, I need to multiply, you know what, let me go ahead and label everything for you here. That first f of x value is x sub 1. The second one is x sub 2. This one was x sub 3. And then the last one was f of x sub 4. So these are the heights of the rectangle. And as you can see, we got the delta to be half for every one of these rectangles, right? So let's go ahead and plug into our formula. First, I'm going to do 2 times 1/2 plus. Where did I get that from? 2 times 1/2, right? So that's 2 times 1/2 right here. And then what's next? I'm going to do plus square root of 15 over 2 times 1/2 plus, next one, square root of 3 times 1/2. And the last rectangle, had a height of 7, square root of 7 over 2 times 1/2 as the width again. So what you can do is you see how all of them are getting multiplied by 1/2. We can factor that out. We can factor out 1/2 and just do 2 plus square root of 15 over 2 plus square root of 3 plus square root of 7 over 2. Now, we should get something very close to pi, though, don't you think? So at this point, I'm not going to spend any more rooms there because I want to do the 8 rectangle in the bottom. Add these numbers together and divide it by 2 for me. So what is 1/2 times 2 plus square root of 15 over 2? And what we should get is something close to pi because we know the area is really pi. Square root of, I'm still typing this, guys. Give me 1 second. Divided by 2. And when I type this into my scientific calculator, this is the number that I got. I got 3.4957. And the next number is 0, so I'll round it to that much. So this is pretty close to pi, 3.14. At least it's like starting with 3. But it's not that good. It's actually bigger, you see. Why do you think this is bigger? Because I'm about to highlight some areas for you. That tiny yellow pieces that's sticking out of the circle. I mean, my area using 4 rectangles was overestimating by adding areas of those yellow highlighted pieces. Those were not under the curve, so understand why it came out bigger. Now, let's go ahead and do the second part. They also wanted you to do the same process, but this time they wanted you to use what? 8 subintervals. 8 subintervals. So I am so out of room here, but it's okay. Let me go ahead and try to make this a little bit smaller. Oh, looking good. Let me try to. Oh, no. All right, let me do that one now here. So I'm gonna draw one more time our picture. It's going from 0, 1, and 2. And I remember it was also going from 0. I don't need 1 there, but I need to start from 2. So it's a circle. It's a quarter circle that looks like that, right? And what they want is 8 sub-intervals this time. So guess what? We're going to have to figure out delta x again. Delta x is going to be, subtract the endpoints, b minus a. And here a is 0 and b is 2. A and b are simply the endpoints of your interval. So 2 minus 0, and we're dividing that by 8, right? So this time, our width is going to be 1/4. So I'm going to have 1/4, 1/2, 3/4 right here, and then 1. And then I'm going to have 5 over 5/4, 6/4, 7/4, and then 8/4 is equal to 2. So that's perfect. I don't like how it's a little bit off. They don't look equal, but maybe I can fix that. Sorry, I think the lesson videos are getting so much longer just because I'm being so silly. I get bothered by little things like that and I want to fix it. Okay. So how many rectangles are we going to have? Now, watch carefully as I create my beautiful rectangles using the left points of each of these. So I'm going to stick out a little bit and come straight down. Here's my rectangle number 1. Here's my second point on that curve. Go straight out and then something like that. On this point, go straight out and come straight down. And that point, out and come back. See, again, we are going to be overestimating because our rectangles are slightly bigger than the curve, really. But I'm just drawing these rectangles using the left points. So, you know, our book doesn't, but sometimes a graph like this, a decreasing graph, using the left endpoints, we're going to end up overestimating. So, but what if you use the right endpoint? That's an option, but then we will be underestimating. So sometimes we use the midpoints to create these rectangles. For our class, we're just going to always go with the left endpoints, okay? Okay, so I have 8 rectangles sticking up. We do know that the width of all these rectangles are 1/4, right? But we don't know about their height. So guess what we're going to do? We're going to have to find 8 different, yes. So find f of x1, which is f of 0, f of x2, which is f of what? 1/4, f of x3, which is f of 2/4, and 2/4 is 50 cents. F of x4 is going to be f of 3/4. And we're halfway there, guys. F of x5 is f of 1. F of x6 is equal to f of 5/4. F of x7 equals f of 6/4. And, oh, you know what? Let me go ahead and change my 6/4 to a simpler fraction, 3/2, okay? Just because. Just because. 3/2, 3/2. And then f of x8 equals f of 7/4. Okay. Now, I said 7/4. Why did I write 7/8? Ah, my gosh, who knows? Who knows? Thank you, Sue, for catching that. Okay. Now we're going to just spend some time evaluating these values at, what was the function anyways? F of x equals, wasn't that square root of 4 minus x squared? Yes. So, guys, I'm going to be doing this. If you want to fast forward the video, that's okay. Because you all know how to do this. But I'm just going to do it right here. So if I plug in 0 in there, remember that was 2. And then I think, remember, the 1 gave us square root of 3. I'm just copying from the line above that we did. We also did half point. Half was 15, square root of 15 over 2. And then 3/2 was square root of 7 over 2. And these are the 4 values that we evaluated on the first part when we did 4 subintervals. But now I gotta do the other ones, okay? So excuse me as I figure these out. 4 minus quarter squared under square root. That's going to be 64 over 4. 64 over 16 minus 1 over 16. Square root of 63 over 4. Okay, next one. Down here, I'll do 4 minus 3/4 squared. I'm making the first fraction 64 over 16 so that I can subtract 9 over 16 from it. And what is 64 minus 9? That is 55. So that little 55 will stay in the square root, but square root of 16 will come out as 4. Yay! Keep going. Next one. This one is 4 minus 5 over 4 squared. Oh, it's a little tedious, but it's okay. It's very, very, I feel happy doing this. So what's that? This one is 64. Whoopsie, what was that? 64 over 16 minus 25 over 16. And if I subtract 64 minus 25, I get 39. So this number is square root of 39 over 4. Yay, the very last one now. 4 minus 7 over, oh no, 7 over 4 squared equals 64 over 4 minus, no, 64 over 16. Because I'm trying to rewrite 4 as a fraction with 16 in the denominator. And this one is going to be 49 over 16. So if I do 64 minus 49, that gives me 15. So I have square root of 15 over square root of 16 simplifies to 4. Yay! So that's it. I found all the heights. I found 8 different heights. Now we're ready to do the Riemann sum. All right, so let me minimize this one a little bit. All right, so let's write down the area. So the area, the Riemann sum, starts from I equals 0 all the way up to 8 because we had 8 subintervals, we had 8 rectangles, and our f of x, I'm going to say f of xi times delta x. Now let's go ahead and write down 8 products, the sum of 8 different products, okay? So the first one I will have 2 times 1/4, right? Now, well, let me write it. 2 times 1/4, what's next? Square root of 63 over 4 times 1/4 plus, I did this one. Next one is square root of 15 over 2 times 1/4 plus square root of 55 over 4 times 1/4. That requires some real dedication here, guys. Square root of 3 times 1/4. Square root of 39 over 4 times 1/4. Square root of 7 over 2 times 1/4. And the very last one, square root of 15 over 4 times 1/4. Okay, so if you do all these sums, but you know what we can do again? All of them are getting multiplied by the same fraction of what? 1/4. So let's pull that out. Let's pull out that 1/4. So our answer will be 1/4 times 2 plus square root of 63 over 4 plus square root of 15 over 2 plus square root of 55 over 4 plus square root of 3 plus square root of 39 over 4 plus square root of 7 over 2. Oh no, I want them in the same line. Hold on. I think I can squeeze it in. Plus square root of 15 over 4. Close the parenthesis. Now, let's go ahead and get that decimal approximation. And guess what we better get? We better get something very, very close to, very close to the pi, right? Because that's the actual area. So, I'm going to go ahead and type this in my calculator right now. And then I'll tell you what I get, okay? 2 plus square root of 60 over 4. And don't worry, the daily problem that you're doing for me, you're not doing 8 rectangles. I think you're doing like 5 rectangles. Not that bad, right? 15 over 2 plus square root of 55 over 4 plus square root of 3 plus square root of 39 over 4 plus square root of 7 over 2. It's not necessarily the difficulty that's taking us forever. It's just the work is hard work. We're doing some good work. All right, guys, I typed it in, and this is what I got. Ta-da! I got 3.3398. 3.3398. 198. 982. I'll just round it up to about that much. So notice we got a little bit closer to the pi, a little bit closer to 3.14, which is the actual area of this area under this curve, then when we use 4 equal size subintervals. So if you really want to get closer and closer, and suppose we're working with a curve that doesn't really have an area formula, like a quarter of a circle, then it's going to be a great idea to create infinitely many rectangles, don't you think? Like thousands and thousands of rectangles, and find the area of them, right? And how are we going to solve that problem? How are we going to actually find thousands and thousands and infinitely many rectangles? Of course, we're going to take limit later, okay? We're going to take limit later. We're not actually going to find 1,000 rectangle areas. So, you understand why it came out a little bit bigger, though, because we were kind of overestimating by adding the area of these gray shaded regions, and that should actually be sticking out there. But because we were overestimating a little bit, I mean, like I said, if you use these left endpoint Riemann sum, then we're going to be overestimating for these decreasing functions. But for our class, we're only going to just look at left endpoint rectangles, okay? All right. I'm a little scared if my video is going to be way too long, but I think we should go on. Let's finish number 7. This is kind of similar to what you will have on your homework. Now, use 5 subintervals to approximate the area under the curve of f of x equals this. If you are doing this homework, because for me, it helps greatly. It helps greatly if I actually have a picture. So guys, what I did was I went to desmosgraphingcalculator.com, and I just really graphed that function. And I played with the scale a little bit. I wanted it to have longer, like a bigger, I should say, the vertical axis. You see how the vertical axis goes from like 0 to 50-ish, and the horizontal axis is going from 0 to 18. And I said that because I saw that we're finding the area under the curve over the interval 1 to 16. So from 1, which is right here, I'm going to go ahead and draw a dotted line up. So from this point right there, all the way to 16, they said. So I kind of created this picture and took a screenshot of it on Desmos. Because it really, I'm a visual person. I got to see the picture. Because if I am cutting this into however many rectangles, I want to have a picture. Now, they said 15 sub-intervals, right? And our interval goes from 1 to 16. So I think we can make it, we can find delta x. So let's find delta x. Delta x, the width of each rectangle is going to be 16 minus 1, subtract the endpoints, and divide by the desired number of subintervals. So that's going to be 15 over 5. So the width of each rectangle is going to be 3. Now I'm going to go ahead and write numbers. Those are which are going to be my left end points of these rectangles. So 1, 2, 3, 4. Oh, not 3, 4. So I'm going to have a cutting points right here at 4, the width is 3 there, right? Because from 2, 3, 4, I have the width is 3. 1, 2, 3, right? Okay. Now what's next? The next number will be 1, 2, 3. The next number will be 7. Next number will be 1, 2, 3, 10. I'm going up by 3. 1, 2, 3. Next number will be 13. And then 1, 2, 3. That will cover the rest of the curve. So let me go ahead and draw the rectangles now, okay? So first rectangle starts right here. And then, you know, when you draw a rectangle, you're not going to go up like that, right? Or you're not going to go like curve. Don't follow the curve. We're trying to draw a rectangle. So straight to the right, come straight down. Okay, so that's the first rectangle, number 1. Now, next one, I need to start on the curve, though. I need to start on the curve. So the second rectangle will go like this. This one is going to be overestimating a little bit. Now, the third rectangle starts on the curve, goes straight up. Now, this guy is also overestimating a little bit, right? Why? Because we're decreasing. We're decreasing. So the left end point that we're picking is going to be highest on any points on this rectangle. Now, from this point, I'm going to go straight to the right and come straight down. Again, I was overestimating. Now, from this point, you can't go follow that graph. Don't follow that graph. Go straight to the right and come down. Now, notice, out of these 1, 2, 3, 4, 5 rectangles, number 2, 3, and 4, they actually have the area that are sticking out of the curve. You see what I mean? That was the interval where the function was decreasing, right? Decreasing. But take a look at rectangle number 1 and rectangle number 5. Okay, number 1 is here, number 5 is right here. Notice in those intervals, the function was increasing, right? So the left end point that we picked, and to draw the rectangle, those rectangles are underestimating the area under the curve. Oh, that's such a fun concept to talk about, but I'm sad that our textbook doesn't really go into more of that. But so again, like we said, we're finding the approximate area. We're not trying to find the exact area, but we know, well, these 3 in the middle will give us slightly bigger value, but 1 and 5, maybe they will take away enough. So this is going to be a good estimate, okay? So let's find the area of these 5 rectangles, okay? So we do know about the width already. All of their width are going to be 3, because that's what delta x is. But now are you ready to find all those f of x? So f of x1 is going to be f of 1. Oh, dear Lord, the function is kind of long. 0.1 times 1 cubed minus 2.3 times 1 squared plus 12 times 1 plus 25. All right, now where did I get this problem? Maybe I got it from the textbook where I can just copy down the numbers because it's going to take me a long time for me to type in these into a calculator. All right, give me 1 second. Because sometimes, guys, when I make up these examples that I go over, sometimes those are from textbooks, sometimes those are from the homework problems. And this one, I'm going to just double check. They didn't really evaluate the function this way, but it's the first number that I see is 34.8. I'm just going to check the first one here, and then maybe I'll just use I'll save some time by copying down from copying down the numbers that the textbook's using. But let me go ahead and just check this one real quick, okay? Oh, you know, the math isn't really difficult. Yes, so that was right. So if you evaluate this, you will get 34.8. Let's keep going. I just need to evaluate how many more? 4 more. F of x of 2 is f of what number? 4. I need to plug in 4. 0.1 times 4 cubed minus 2.3 times 4 squared plus 12 times 4 plus 25. And that should come out to be 42.6. That should come out to be 42.6. Now, f of x3, well, which is f of what number? 7. That's the third x value, right? It's going to be 0.1 times 7 cubed minus 2 times 3 times 7 squared plus 12 times 7 plus 25 equals, and that should come out to be 30.6, guys. All right, f of x of 4 equals f of what number? 10. So we do that. 12 times 10 plus 25. And that will be 15. And the very last one, let's do the very last one. F of x of 5, which is f of 13. Notice we're not using the endpoint 16 here because we're using the left endpoint to create these rectangles. 0.1 times 13 cubed minus 2.3 times 13 squared plus 12 times 13 plus 25. Thank goodness I know the answers for these from the textbook. So that's 12. That's 12. Now we're done. We're finding all these f of x. We found the height. Now you're ready to find the Riemann sum now. Let's go ahead and give them the area. So summation notation as I goes from 1 to how many rectangles do we have? 5. F of x of I times delta x equals, now let's kind of do this, because I was going to do this. I was going to multiply 3 times 34.8, 3 times 42.6, 3 times 30.6, and just add them all together. But you know what? They will all get eventually multiplied by 3. You know that now, right? So we're going to just factor out the 3. We're going to just factor out the 3 and add up the height. Okay, add up the height. So 34.8. So you know the idea is like this. We got equal width rectangles, 5 of them. We're basically sticking them up on top of each other to make a super long rectangle, right? And that works because they all have the same width. Plus 42.6 plus 30.6 plus 15 plus 12. So we're adding up all the heights, but since they all have the same width of 3, I mean, mathematically, we're factoring it out. But if you imagine putting these rectangle 3, 4, 5, 2, 3, 4, and 5 on top of rectangle 1, we're just going to create a very, very tall rectangle. And that rectangle will have a height of everybody added together. So go ahead and type that in. Feel free to do that. I got the answer right here. It should come out to be 405. 405. So that's how we can approximate the area under the curve using Riemann sum method. And this is going to be a great starting point. Next section in 4.3, we will kind of move away from this area. Well, we'll do a little bit more of area and definite integral, I think, in 4.3. But in 4.4, let's talk about some properties of definite integrals and try to sort of move away from this graphing and rectangle method, okay? Alrighty, that's it for 4.2, really. Thank you for, going through slightly longer lessons just for the next couple weeks as we are trying to finish everything, because I don't want you to go up to Calculus 2 not knowing parts of Calculus 1 and be behind. I want to make sure that I teach everything, even though we lost some days because of all this corona stuff. So try 4.1 daily problem for me. Oh, no. 4.2 daily problem, which is about, try to click on it. Come on. But it's just hard for me to click on this on iPad. But that's the one, oh yes, this one, open link. Yep. I got the picture there for you. Again, it's a decreasing function. It looks like, I don't want to assume that it's a perfect circle. Don't try to use the area of a circle here. Use the Riemann sum method. Find the area of these 5 rectangles and then add them all together, okay? All right.